So Solidity is an interesting topic. So first off, Solidity is very simple. It is a it's an object-oriented C-type language, and it's only halfway good. It's not even that great of a language. So with that, we can call this to an end. But oh no, what's super interesting about it is the fact that it is the primary language that people write Ethereum smart contracts in. So Solidity itself has some interesting bits and pieces, and it's not super interesting in a vacuum as a language, but it becomes very interesting in the ecosystem that it lives in, right? So before we talk about Solidity, we need to talk a little bit about the context around it for a second, and then we'll dive into actually writing some Solidity, hopefully. So first off,
I was going to say, do you need to share your screen or is that
not yet?
Okay.
We will get there. So first off, let's talk blockchain for a second. So first off, blockchain is interesting in that, I need a host to enable screen sharing. I don't know who's a host.
I can do something here. Hold on.
You're good.
Hold on.
Yep,
Am I
you're
a
good.
host? Maybe. Wait, no, I'm not a host. Oh, I have to sign one. Oh, geez. All right. I have to sign one.
While you're getting that, you're fine. Blockchain has some interesting pieces in that you can ask this great question and you can say, hey, what is there when it comes to blockchain? What is there that is real on a blockchain? And the interesting answer is nothing, because of forks. I'm tuning forks this time. Anyway, so there's a couple of different types of forks in the blockchain ecosystem that we need to kind of have as context around the Solidity language. So first are these major forks, or hard forks, they're called. So we've got a couple. We've got the initial launch, and then there's these forks that happened at various points in time, which is effectively points in time at which people decided to do something differently. And so in the case of Ethereum, we see technically there are these, let's actually talk about some specific forks like Istanbul and Constantinople, or St. Petersburg. These are forks that the Ethereum ecosystem all decided to do, and the majority, the consensus, which is a big word that gets used a lot in blockchain, the consensus is that everyone decided more or less to agree to make a change to the core system of the blockchain together. Sometimes that change isn't agreed on by enough of the majority. And you can see here, this is the DAO hack. This is a big point in Ethereum history, but it's a point at which a large enough portion of people decided to keep going with technically not to fork is the interesting case. It shows it here as an Ethereum Classic as if it's a fork. The reality is Ethereum Classic is the original and Ethereum is the fork. Because Ethereum Classic decided not to fork. They decided not to apply the change that rolled back the DAO hack. But the important part is that there is merely a consensus that when you go to Ethereum, if you go to Etherscan here, this is a block explorer, and we look at the latest block, the idea that this is actually the latest block is merely because a lot of people think it is. And if a lot of people thought something else was the block, if more people thought something else was the block, then that would be the block. So as you're building up this log of data, right, effectively whatever the majority, now you could ask, who is the people from which this majority appears? And the answer is well, it depends. But actually, at all points in time, while you're working on Ethereum, there are forks being made, little tiny forks happening all the time. Which is why if you ever tried to do anything with cryptocurrency, you might have heard about the concept of confirmation time. And that's kind of this time of, well, you probabilistically are more likely to be in the consensus if it's been around a while longer than if the data hasn't been around that long. Now, this is very confusing from a lot of traditional computing and traditional environments, which is where you either know that something's the case or you don't. You either know that it's consistent or you don't. In the case of blockchain, what you generally get is you get eventual high probabilities that something is true. But technically, someone could go back in time and actually make a new fork. They could say, well, Ethereum went wrong all those years ago, back at the Ice Age. The Ethereum went wrong, and we're going to make Ethereum super awesome, and we're going to start back way back here. So that's kind of this context of blockchain that we're going to attempt to program a virtual machine within, but it also leads to more than just a programming language in that you're dealing with this consensus of data behind all of it. So it's not just a matter of I'm going to make a program and I'm going to run it in this isolated environment. It's being run in the in whichever fork environment that it exists in. Now, of course, you can also create your own. You can that you can run a test net. There's other things you can do with that program, but understanding that the program runs within the context of its history is critical to being able to work through Solidity. But Solidity is technically not the language that the Ethereum virtual machine actually works in. So this is the famous Ethereum yellow paper. Currently, this is the July 11th of this year, the Istanbul version. The London hard fork is coming up later this month, I think.
September something, yeah.
Yeah. It's not specifically timed because we'll talk about time and blockchain is an entirely different talk, I think, actually. But here in this, we actually have all of the commands in the appendix. We have these are all of the this is the fee schedule. Everything that you do on Ethereum costs some form of gas. This gas is any operation that happens on the blockchain as far as writing to the blockchain goes, costs gas. And you actually have to say how much gas you're willing, the maximum amount of gas you're willing to spend. Because Ethereum virtual machine allows you to write Turing complete programs on it, that means you cannot know if the program will halt. It does not necessarily have a halting condition. So we use gas on Ethereum to make sure that we know eventually that program will run out of gas. And so it will halt because of gas operations, not because, and fail probably, but not necessarily fail because it doesn't have a halting condition. You can definitely write in Solidity, you can write an infinite loop. That infinite loop will cost you a lot of money, and then the transaction will fail because the infinite loop is still going, and you just waste money. But all of the interactions on the blockchain have different commands that can happen. And so we have things, I thought I saw the, That's the, where'd the commands go? Anyway, the fee, I thought there was a list, a reference list somewhere here, but I can't find it off the top of my head. But there's ones like you can load into memory and you can pull out of memory. We have things like equals. It is a stack-based language that the EVM runs, and Solidity compiles down to the bytecode for it. And it actually has access to, Solidity has kind of a sub-intermediate language called Wil, which actually is much closer to the, we'll show that off here real quick. This is actually much closer to the actual code that is used on Ethereum. This is, it's still, it's a mid-level language. It's not quite assembly, but it's close. And so we have things like switch statements, but we also have really basic levels. Where's the, we have basic things like less than, greater than, and that is all operating on a stack. We aren't going to get very deep into the stack. We might be able to show a little bit, but let's get to actually looking at some Solidity code. So here is, this is the Ethereum, this is Remix, this is an online IDE, which works pretty well. And this is a very basic storage contract. What it does is it says we have a standard variable for our contract, and we have a way to store that variable. It's that is public, so we can store it. And I don't think there's actually a way to retrieve the value, unlike this doc says. But we can actually take this. Let's compile it. And we can actually take a look real quick here. Here are the actual opcodes involved with this action. And this is the entire, this is the actual bytecode up above. But the opcodes are, first it's saying, hey, I want to push this into the stack. Here it's taking the call value for the actual function, duplicating that, checking to see if it's 0, and so forth. And here we're actually doing a jump. And we can actually see way down here, there's actually, this is the actual function, believe it or not. This is the name of the function, and it's saying, hey, if you called the name of the function, we're going to jump to 30. So very simplistic, low-level function. And Solidity makes it so we don't have to worry about that for the most part. Instead, we can just write standard object-oriented code, just like you're used to doing all the time. So before we go too much further, are there any questions? I have the chat up if anybody has any questions, but we can also do yield hands. All righty. Then we shall carry on to storage. So when we're storing data, there are actually, believe it or not, there are 3 different places in the Ethereum structure that you can store data. And this is important because anytime you store data, it costs money, right? Again, we're dealing with this case where every single one of these opcodes has a cost to it. When I do push one, when I do mstore, when I do call value, each one of these things has a cost to it, because each one of them is going to fall into one of these operation fee schedules. So, for example, push, all of the push ones and equal, it's a very low. And if we look up here, it's very low. So very low means it costs 3 gas for each one of those interactions. So 3 gas, I forget what jump is, but this is 3 gas. This is probably 3 gas. And as you can imagine, those 3 gases and the more expensive ones, they stack up. So it's important to think about when you're interacting with data, because of the cost, it changes how you program. This means that while in a typical language, you might try to program something efficiently for speed, or so it's easy to read, or for a myriad of other reasons, you might try to organize your code in one way. In Solidity, you only have one thing that you're optimizing, and it's going to be how much gas does it cost to do the interaction. And that leads to some really strange setups. So when you're actually storing data, you have 3 different types of data storage. One is right here. This is just standard contract storage, and it is persistent. Again, remember, this is that context in which we're writing the program in. This data will be, if I call this function, I'll pay a lot of money, and I will store that value on the blockchain, and it will be accessible and readable to anyone who wants to see it. However, this Y value here that's coming in to the function is also stored. So this is called data storage. This is the data that you call the function with. Because the blockchain, in the case of Ethereum, allows you to validate every node out there, which there are currently about 9,000 or so last I counted, or I didn't count personally. Last I checked. There are about 9,000 nodes in Ethereum, and when someone calls store A on this smart contract, what's going to happen is it's going to save that value. It does not save necessarily, it's a little fuzzy, but it doesn't necessarily save the X value. It merely saves, hey, someone called it at this time with this value. And the nodes are going to be efficient and keep track of the current state as well. But what the core of the blockchain, the transactions that are happening, is actually storing this data right here. That means that even though I'm not paying to store this Y value forever, let's say if all I cared about was storing that one Y value, this function right here, it doesn't look like it does anything, but it does, because in the transaction, when you call this as a transaction, this Y value will be saved to the blockchain. Not easily accessible, I should say, but it will be saved to the blockchain. So if all you want to do is store data on the blockchain and be able to read it out from the blockchain later, this is a perfectly legitimate way to do it. However, it won't be accessible to future smart contract calls. The only way to do that is by storing it in contract storage. So we have call data storage, where you can store the data in the call data, which is not terribly efficient. We have data that you can store for future smart contracts to use. And there is a third type of storage called an event log data storage. So this is data storage that we're not going to go deep into, but it ends up being used a lot. And so, but that's data storage is data that is easy to access from the outside, and it's much more parsable, but it is not accessible by the smart contract, future smart contract calls. So we'll see some of that in a little bit. So those are our different types of storage. Rico?
So is there any advantage to like, why would you say it's less gas for you to store a call versus an actual stored constant value?
Yeah. So this costs several orders of magnitude less than storing the data here. And you can't get away without storing, like you can't call without having this data. And so storing it in a log, which is still several orders of magnitude less than storing it here, is still somewhat expensive. But yeah, it's all about cost. Ari?
Sorry, it's kind of noisy in here, but do people write these programs in Yule or even in the opcode directly in order to make it more efficient?
Sometimes is the answer. There tends the Yule, the kind of intermediate language, tends to be fairly common for like small snippets of code.
Oh, so you can embed.
You can embed it, yeah.
Oh, yeah, that's cool. Can you edit the compile? You can like compile it down and then edit that.
So you can also do that, but here is just some inline assembly where I'm doing something. This is for my for the client. This is all open source code. But this is a little bit of code that you can't easily do in normal Solidity, but you can do breaking the rules. Obviously, the linter does not like you to do this, and you can do it there.
Oh, cool. So the assembly is Yule then.
In this case, it's considered Yule. Yes.
Yeah. Okay.
But you can.
Okay, go ahead.
You can kind of interact with it. And then at some levels, people actually will go all the way to where they're actually working directly with the opcodes.
Yeah.
But it tends to be only on super. Not right now. It tends to be only on. Not right now. I know. When mommy gets back, you can have a snack. Okay, so but there are some cases where people will get super, if it's something that you really want to be super optimized, you can go all the way down to those opcodes. But it's not very common.
Does the Solidity code get written into the blockchain, or is it just the opcodes?
It's only the bytecode. So only those opcodes get get all the way down to the blockchain.
Yeah.
So if you actually go look,
that's interesting.
If you look on Etherscan, for example, you'll see that there are people who have done contract calls. Let's see if we can get one here to load up. And the service is unavailable right now.
The thing you did earlier, he might be able to see that. You had it in your editor.
There you go.
In Remix, yeah.
Yeah, so this is the actual, this part right here is what's actually being written to the blockchain. But this is the opcodes that compile to that hex.
So that doesn't get, it's only the hex that
it's only the hex
up in there. Oh, okay.
That ends up in there. You can then decompile that to opcodes.
So that, yeah.
And Etherscan allows you to say, hey, I can validate on the blockchain explorer that a particular contract, if I get one, that a particular contract is that the Solidity code would create that contract code. So if you have the original source code, you can then validate it. Decompiling it is, you can definitely read it if you want at the opcode level pretty easily, but it's not super easy to read until you get super used to it.
Yeah. Well, thanks.
Yeah. Alrighty. So we're gonna do what everybody always wants to do, right, with a blockchain. Can everyone still see my new editor? All right, I'm never sure if when it switches, you can see it. We're we're going to write ourselves a token today. So this is the interface. This is the standard interface over here for the ERC20 token. So there's Ethereum. There's Ethereum improvement protocols, which were previously Ethereum. I forget what ERC actually stands for now when they changed it to TIP. That's the old term, but this is an interface that someone said. So there's different types of improvements. You can make improvements that actually require you to change the code of Ethereum and interact in a different way. And there's improvements that say, hey, here's a standard way to do something that everyone else should do. And some of those take off, such as the ERC20 for the ERC20 token. So this means we have to do a couple things. So let's just start off with this one here. We need to know how much supply we have, right? And we need that supply to return ourselves a uint 256. How much of this token do we want to create? So let's just add a uint 256. And let's call it total supply. Nothing terribly special. And then let's just say, hey, this one right here is just gonna return total supply. There we go. So, standard everyday programming, right? Let's go grab we need to be able to show what the balance is. So an Ethereum address. So this is starting to get into the interesting parts, more of Ethereum than anything else. But addresses on Ethereum all exist. You just haven't found them yet. So you want that person that has a whole bunch of money in their account. They didn't actually create the account. They merely discovered the private key that controls that account. You too could discover that private key. It'll just take a long time. Ari?
I was going to ask, do the different numeric types have different costs?
That's a good question. Yeah, they do, but it's more than just that. So Ethereum stores its data in blocks of 32 bytes. So 256 is a block size. And so you can do things like, if we create a function here, if we created one that was a uint 8, and then uint I don't know why I always want to do that, uint 8 y, and let's say uint 250. So this is going to take up two memory blocks worth of data, and that will cost different than, for example, if we were to move this one to the middle. We have one memory block now, 2 memory blocks, and then we actually have to have a 3rd memory block. So even the order of the parameters ends up mattering. This is why you end up with some really weird smart contracts. Because that's the type of code you would never necessarily write code that was, if this was Y and this one was Z, right? You would never want to write it this way, but it may be more efficient for Ethereum to do that.
Yeah.
I do know that if this were like a library I was pulling in, and even if it didn't do a whole lot.
And Rob mentions people been leveraging IPFS to store data versus storing it on ETH, the ETH blockchain. That is indeed a very big cost-saving measure. Durability, I'd say actually Ethereum is a little bit safer in that the Ethereum, if you stored it in Ethereum, it's going to be stored for as long as the Ethereum chain is around, at least the current setup. But it's a big cost saving measure. And usually then you just store a hash, which is, I think IPFS hashes are 32 byte, if I remember right. That may not be. But let's go back to our token. Great questions. So I want to be able to say, I want to have a balance in an account. And remember, all accounts already exist. So there's actually a nice data structure. This is one of the more unique things, is we have a mapping, and we can map addresses to, let's do uint 256 still. Maybe somebody owns every single token. And so these are our, let's just call it balances, right? So we have our balance, and this is fun in that we can just say return balance account. And we are now, this mapping, this is a sparse mapping. So every address already exists. There is no null or undefined. It is merely 0. And so 0 in Ethereum has, and therefore in Solidity has some very interesting properties. This value, right? We don't just say, hey, I need to initialize all the billions of Ethereum addresses. They all exist and they're zeros. We don't have time today, but there's some really interesting back-end memory structures of how you actually, how Solidity is actually taking this mapping and mapping it to an actual memory space. Because it actually still has to have a memory address behind all of this data. This one is actually memory address 0. This, however, ends up with a couple pointers, doing some actual hashing to create pointers on the fly, so that you can't, you probably do not interact with your own data incorrectly. You end up in a lot of cases where you're actually ending up having to manipulate some of the data structure, the memory locations of your data in order to properly use it. There's this interesting case where, because you want to save money on data storage, and saving anything to the blockchain costs money, it means you want to reuse data on the blockchain. You want to reuse code that's on the blockchain. There's actually a couple ways to do that, like libraries, but there's also a way that you can actually say, I want to just borrow that smart contract. I want to borrow their logic and just do their logic in my memory space. And so where you're actually memory addressing ends up coming up a little bit more often as to, well, where is it going to be addressed to? Because you may not be necessarily interacting. You can write code that is designed to interact inside of someone else's memory space. And you don't want to collide and accidentally say someone has a balance when they don't, for example. So there we go. So we got a basic balance. And now we can do, here we go. We got a transfer. We want to take some money out of the recipient. We want to send some money to the recipient. And this gives us a piece that we have there is a universal message object. So this message object is the data that comes with the transaction. So we have, for example, we have the gas, we have who the sender is, which is very important in this case, right? So we're going to say, we're going to require that the balance of the sender is greater than or equal to the amount being given. Not enough money. So require basically requires this to be true, or the blockchain throws an error effectively and says, nope, can't do that interaction. So now that we've guaranteed that it has enough money, we can take the amount out of the sender's balance, right? Standard kind of, yeah, not, you can do almost that exact same thing in JavaScript, right? And we're going to give it to the recipient. And we have to return true for the interface. So there we go. So that's, you know, again, nothing, we're not doing anything crazy. This is what, you know, some people I think laughed when I said at the beginning, Solidity is not a very interesting language. And it's not. Like, it's the same stuff you're doing in every other language. Lindsay?
So I guess, of course, the question I must ask is this an atomic operation?
Yes, it's that context, right? So the answer is yes, with a slight waiver on yes. Remember when we talked about forks? The problem is that there's a couple issues in that your let me get back to here. Yep. So let's say you're right here, right? You're right after this change, and you sent someone some money, and then someone else decides I'm gonna see if your money is available to me on Ethereum Classic. But the answer is if you are after this dot, then you didn't send them any money on Ethereum Classic. But if you're before the dot, you did. So it makes for this case where, right, when you have these little tiny forks where it's like you can end up with one section of the network, right? Because we talked a little bit when you consensus, but consensus of whom? And the answer is consensus of everyone who consents. As that, right, you don't know about the people you don't know about. So let's say you are in a consensus of 100 nodes. Well, you're probably good.
Well, I
But
guess I
yeah.
was talking about like the operation itself. Like, is it possible that part of that function executes and not the rest of it?
Ah,
So like, is it possible
no.
for line 20 to occur and line 21 not to occur?
It is not. It will either all happen or not.
Okay, yeah, that was what I was mainly
Yep, sorry.
asking. So like,
Yeah.
okay, so function calls are like always atomic in some important transaction-y sense that we need for these things to make sense.
Correct. What they don't necessarily do though is come in the order you expect them to. Like if I give money to two different people at the exact same time, they could end up in two different forks. They could end up in different orders, and you can so it all happen in some places and not happen in others, but eventually the consensus would say that it all happened, and probably everyone would agree. And again, if a minority of people disagree, then they're not in the consensus, and we don't have to worry about them. The problem is when you have when you're in the minority and you thought you were in the majority.
Okay.
Is that where that thing from Silicon Valley, the 51% comes
I
from?
have not seen it, but yes, that's the 50 plus person. Yes, always important. Some blockchains handle that differently, I should say. Ethereum requires 51%. So if you control 51% of the nodes, you can do whatever you want. You can mark invalid transactions valid. You can change history. It's all up to you. Some networks only require 33% of people to do that. That's a good one, Lindsay. It's this question about like, who do you trust, right? If you ran your software, if you ran your JavaScript right now in a browser on someone else's computer, you trust that JavaScript is going to do what you told us to do. But there's no actual guarantee of that, right? You're running on someone else's computer, they could have a debugger thrown in there and they could alter the variables, right? I even do that intentionally sometimes, right? So someone had a password. They let me reset the password to longer than 15 characters, but then I couldn't insert a password. of longer than 15 characters when I needed to log in. That was a very tricky thing to get around. Fortunately, it was not server side limited, but the same thing happened. The big difference here is, right, your smart contract code is going to run on all these different nodes, and they're all, in a way, they're all comparing the result to each other to make sure that they're correct. So unlike when you're running JavaScript on someone else's computer and you have to trust that their computer is doing what it is, or even, right, recently, right, running it on your own computer, trusting that your virtual machine's not hacked, or your CPU isn't actually like, some, international entity hasn't somehow gotten into your hardware and starts flipping bits all around. Here we have a level of consensus that we're probably, you should be paranoid. It's not paranoia if you should be. But here we have a consensus that if 51% of the people, again, people that you know about, agree that you're probably all right. The kids, the transactions are all right. We're going to skip over a couple of these other functions in that they're not super interesting. We're going to instead see, we're going to do, how am I doing on time? 3:32.
13 minutes left.
13 minutes. All righty. We're going to look real quick. We're going to do a transfer event. So this is an event. We have access to it. Anytime, according to the EIP, anytime I do a transfer, I also need to emit an event saying who it was from. In this case, message dot sender, who it is to, the recipient, and the value, except without that. So this is creating this kind of log data that's and it's indexed, which allows us to easily go into a block explorer and ask different nodes about the data. And I can say, hey, give me every transfer event where somebody with this address sent money to anybody else. This is this kind of data that's helpful for distributed applications, for DApps, for applications built on top of blockchain, to be able to access data and interact with data, with it being not difficult to access, right? Like all that data is still here, right? The recipient and the amount still in this call data, but it's not easy to access. This is. However, watch this. Let's play around a little bit more. Let's put up an address up here. Let's call it the owner address, right? We probably need a constructor over here, right? Constructor. And so we need to have, like, what's our total supply going to be, right? Total supply, and we need to have an owner. So we can go ahead and set our, total supply to total supply, right? Standard kind of stuff. And let's set our owner to owner. And now let's just do this. So now, yeah, Ari, go ahead.
Sorry if I'm asking too much questions.
You're good.
Do people hard code the addresses and the scripts, or is that frowned upon? You're supposed to keep that formatting because of the, like you said, the whatever blockchain readers or whatever. It's just frowned upon. I don't know. I'm just curious about that.
Yeah. So a constructor in Solidity, a constructor runs at, when you deploy the contract, you would put in a total supply and an owner address, and then that is written into the bytecode. The constructor logic itself never goes onto the blockchain. So that constructor logic, if you set, hey, if you say, hey, I'm the owner, and it's going to have 100 tokens, that's actually going to get written into the bytecode, just in that raw value. The thing is, though, is here suddenly we said, hey, when I send something to someone, right? The blockchain, interestingly enough, right? Remember, this is all of this turns into bytecode, fairly difficult to read. This is designed to be super easy to read.
Yeah.
So, you know, obviously someone might catch it over here, you know, when someone checks their own balance. But a piece of code like this is the kind of the critical thing. And this is a big, when we talk about NFTs, which we won't have time to do today, but there's a lot of NFTs use these kind of events to kind of track data and track who created an NFT. And if you don't trust the original code, right? It's all there in bytecode for you to read. Good luck. But if you don't trust it, then it can be doing all kinds of crazy things. But let's not go that far. Let's just say this is a setup where, let's say we want to alter the economics some, right? We basically built a standard, like we built a token. That's great. Like we have a supply of tokens. We have balances that people can get to. People can send money to each other. That's all great, right? But let's do something fun, right? And this is the comes down to the real kind of, I think, power of blockchain, is this ability to create entirely new shared consensus trust based economics with entirely new systems. So let's say every time you move money, we're going to give myself one. There we go. And right, total supply. We're going to increase the total supply. There we go. So now every time people move money around, I don't care why, we're going to give myself one token, one carbon token, and we're going to just increase this, tell everyone that the supply is increased. Now that may sound like, well, why would you ever want to do something like that, right? That sounds a little iffy. Let's make it a little bit more realistic. Let's make a fee, right? We're going to say it's a UN 256 still. We're going to say there's a fee of one token anytime that you transfer money. Okay. And so now, right, it's not just, so the sender now has to have at least the amount they're sending plus a token, right? We're going to subtract, we'll do it this way to make it nice and clear, right? Amount plus one, right? There's our fee, or we'll actually use our underscore fee, shouldn't I? That's why I created it. There we go. So we're not going to do this right now. So there we go. Now anytime you send money, the sender has to pay an extra token to send money. But you know what? That's not necessarily super good. Let's make both of them pay money. Let's make both the sender and the receiver. So the recipient plus the amount that they will have, right, has to be greater than or equal to the fee. Otherwise, not enough money to pay fees, right? And so we're going to do the balance minus the fee. There we go. So now we're collecting fees on both ends. And that's all being changed, right? In just a few lines of code. We want to do something new. Let's do this. Let's say we don't like that fee. Let's make it so that the owner can change the fee. No. We're just going to say, hey, require the message.sender to be the owner. Go away. Oops, come on. Feel like I'm typing something wrong. And then we're going to say, hey, we're going to put the new fee, uint 256, new fee, right? And we're just going to say, hey, there we go. So now suddenly we've given someone authority to change the fee. We could also say, hey, we could also do a voting system that token holders over a certain period could vote to change the fee. There could also be a level of burning where they don't, not only do they, right, we actually, we're saying, hey, their balance is, we're removing the fee, right? We actually made a mistake. We didn't change the supply. That's what we missed, right? The entire supply goes down by that fee, or we could increase the fee. Rico?
Quick, I just noticed that these are okay. I was trying to see how you were able to access some of these variables globally, but it's all within the contract. Got it. Because I noticed the word fee was sort of being tossed around in different methods. And okay, I see it now. Sorry about that. Question revoked.
You're good. Yeah, there are some ways to do like libraries and do other kind of access to other contracts. You can actually call a contract inside your contract. We got just a few seconds left. I'll show. This is a code base of all the smart contracts for my client for the current version of the decentralized social networking protocol. And here we have some contracts. We have some much more complex contracts. You can do, this is a contract, for example, it implements 2 different interfaces. And here we actually have structs, which are possible to do as well. We have ways to do storage. We have this is actually specifying the specific memory slot, the memory address for this data to go into. We have these are constants. We have, bit shifting. All of those are kind of available to us. We have some casting. This is casting some enums. We have modifiers. These are effectively little, these are C-style macros. So you can say, hey, I actually don't know if I'm actually using that anywhere. But you can add a macro to things to require them to be, it's being used on something below it. But you can have a macro that says, hey, it requires the stuff to be initialized before it can be used. That get added.
We're kind of running. We got 1 minute.
Sorry. With that, any questions? Last questions?
Do you have a good resource for like reading like source code that like costs people, something like $600 million? Just making up a totally random number that didn't occur in the news at all.
Yeah.
Like I'm kind of curious, like what the bugs look like in these smart contracts, and
yeah, the best kind of way to look at them, Etherscan. If you know like which transaction is, you can actually search for the address or the transaction that did it. And so here, for example, some of them have been claimed, but here's the OpenSea contract that you can actually go look at. And you can actually, in this case, we have this verified. Etherscan.io they uploaded their Solidity code, and they know that if you compile it with this exact version of Solidity, it will produce the code, the bytecode that you see on the actual blockchain. So here's a way which you can actually go and look at and see, oh, it's using safe math. Here's the ownable part of the contract. You can actually take a look at all the code that they use.
Okay.
You can also go and look, for example, here's the ERC 20 token transfers. These are the events just like we just created right here. They could be lying to you. There's no guarantee. There's no guarantee that they aren't lying to you, but you can see it and you can actually go in and look at each individual. Here's the token. So this is kind of the easiest way to actually go look at an individual contracts code. If they don't have a validated version of it, it does allow you to do attempt to do a decompilation, which can be
Okay.
helpful in some cases, but not all.
Cool. Well, thank you, Will, for talking to us about Ethereum and Solidity. I guess we're going to meet in 3 weeks, and Sam is going to be talking about a language that hasn't been decided yet. Sam's not here, I guess, but I look forward to seeing you all in 3 weeks.